Astronomers estimate that the universe may contain as many as a septillion stars. That's one followed by 24 zeros.
Our Milky Way alone contains over 100 billion, including our best-studied star, the Sun.
They are giant balls of hot gas, mostly hydrogen, some helium, and small amounts of other elements.
Each star has its own life cycle, ranging from millions to trillions of years, and its properties change as it ages.
First, let's know how stars are born.
Stars form in large clouds of dense gas and dust called molecular clouds. Molecular clouds range from 1,000 to 10 million times the mass of the Sun and can extend for hundreds of light years.
Molecular clouds cool as gas condenses, forming high-density pockets. Some of these clusters may collide with each other or collect more matter, strengthening their gravitational pull as their mass increases.
Eventually, gravity collapses some of these clusters. When this happens, the friction heats the material, which eventually leads to the development of a protostar, a baby star. Batches of recently formed stars from molecular clouds are often called stellar clusters, and molecular clouds full of stellar clusters are called stellar nurseries.
Now I will know about his life.
At first, most of the protostar's energy comes from the heat released by the initial collapse. After millions of years, the immense pressure and temperature in the star's core fuses the nuclei of hydrogen atoms together to form helium, a process called nuclear fusion.
Nuclear fusion releases energy, which heats the star and prevents it from collapsing further under the force of gravity.
Astronomers call stars stable through the nuclear fusion of hydrogen into helium main sequence stars.
This is the longest period in a star's life. The star's brightness, size, and temperature will change slowly over millions or billions of years during this phase. Our Sun is roughly midway through its main sequence.
Because a star's gas supplies its fuel and its mass determines how fast it moves through its supply, low-mass stars burn longer, dimmer and cooler than very massive stars.
More massive stars must burn fuel at a higher rate to produce the energy that keeps them from collapsing under their own weight. Some low-mass stars will shine for trillions of years, longer than the universe has currently existed, while some massive stars will live only a few million years. At the beginning of the end of a star's life, its core hydrogen is depleted and converted to helium. The energy produced by fusion creates pressure inside the star that balances the gravitational tendency to pull matter together, so the core begins to collapse.
But squeezing the core increases its temperature and pressure, causing the star to slowly expand. However, the description of the final stages of a star's death depends strongly on its mass.
A low-mass star's atmosphere will continue to expand until it becomes a subgiant or giant star when fusion converts helium into carbon.
This will be the fate of our Sun in a few billion years. Some giants are unstable and pulsate, periodically inflating and ejecting some of their atmosphere. Eventually, the outer layers of all the stars blow away, creating an expanding cloud of dust and gas called a planetary nebula.
All that remains of the star is its core, now called a white dwarf, roughly Earth-sized stellar cinders that have cooled slowly over billions of years.
A higher mass star moves further. Fusion transforms carbon into heavier elements like oxygen, neon, and magnesium, which will become the future fuel for the core.
For the largest stars, this chain continues until silicon fuses to iron. These processes generate energy that keeps the core from collapsing, but each new fuel buys it less and less time. The entire process takes only a few million years. When silicon fuses with iron, the star's fuel runs out within days. The next step would be to fuse the iron to some heavier material, but to do this requires energy rather than releasing it.
The star's iron core breaks down until the interstellar force slams the brakes, then restarts.
This change creates a shock wave that travels outward through the star. The result is a massive explosion called a supernova. The core survives as an incredibly dense remnant, either a neutron star or a black hole.
Cosmic material from supernovae and other stellar events will enrich future molecular clouds and join the next generation of stars. Okay, so thanks for watching this video and please subscribe to the channel. See you soon in another video. Till then, stay healthy and stay well. Bye bye.